right, guys, since so many of you are going to be gone for hydraulic jump day, I reconsulted with the stars, and so we can reschedule it for Tuesday, April 4th. It's kind of like astrological signs have to be all lining up correctly to decide what day to have it. And it looks like Tuesday the 4th will still, everything will be in alignment for that day. So hopefully your Virginia conference hangovers will all be finished by the time Tuesday rolls around and you're able to participate. So let's look at some of these other announcements here. All right, so Thursday you've got homework 10 due. And this homework 10 and 11, this is one that previously was just one monster in the past, but I split it up into segments. And so we've already covered some of the material you need to do homework 10. We'll get to the rest of it today. But then the Tuesday after spring break is going to be a big one because you're going to have the second half of that assignment due and then also the exam. So that's just, you know, the day after you get back from spring break. Now, I'm wondering, I'll let this be a majority vote. Do you want a water gems question on the exam? My perception is that probably after just spending the last several hours working on water gems, you know it pretty well, and it could only help you. But then you have to have it installed on a computer that you can bring for the exam. So, you know, I don't know if that balances out your enthusiasm. So what do you think? Raise your hand if you do want a water gems question on the exam. So you're going to have an exam either way. So this isn't like no exam versus exam. This is yes water gems or no water gems. So I don't see very many yes water gems. Oh, come on. This doesn't have to be a whole discussion. It's going to be me asking you a question where you use water gems.
Just like a reservoir of pipe.
I'm not going to tell you about the question before I give it to you. 1, 2, 3, 4, 5, 6, 7, I don't know, 8. It's kind of split. I'll ask again on Thursday. It's not decided yet. All right. You will definitely have paper calculations. So we'll talk more about whether you want to have water gems included on that. I see it as kind of a freebie, but maybe you don't see it that way. No. All right, so today is a marathon session. This is a lecture that really should be split in two, but unfortunately there's just so many weeks in a semester. So my solution to that is some of the examples that normally I'd like you to solve on your own, I'm just going to show you the calculations and we'll work through it just by looking at the PDF rather than you actually crunching the numbers on some of those. Unfortunately, that's the compromise that we're going to have to make. So this is a really important subject because if you think about the reality of rivers, they're constantly changing width and there are always going to be all sorts of contractions and steps that are potentially choking flow. So remember, just to review where we were at last time, we have a step up. And what the step up does is it removes some of the specific energy that used to be available downstream. And so it's going to change the flow depth at location 2 because it's removing some of that specific energy. And we can make the step get progressively bigger. And what that does is it makes the new downstream depth Y2 even shallower as you gradually increase delta ZB. But there's some limit. You can't just keep making delta Z larger and larger and larger because once you make the depth equal to the critical depth at 2, it can't get any shallower to convey more flow. And I'll remind you of something I've said before, and that is that the critical flow is the most efficient depth for conveying flow at a certain energy level. So the minimum amount of specific energy that we can get this much flow through there before choking occurs. And so if we make delta Z even bigger than this critical height, what it's going to do is it's going to cause choking upstream. So we're going to take a look at an example today of this choked flow. Now remember that when you have critical conditions that the depth accounts for 2/3 of the specific energy and the velocity head accounts for 1/3 of the specific energy. That shortcut's going to be useful to us today in some of the calculations that we're going to look at. Okay, now here's the specific energy diagram that illustrates that same progressively larger delta Z. And the maximum height that you can have is the height that takes you from whatever your initial energy level was at 1 down to the minimum specific energy. But then any step up beyond that is going to cause choking because there's simply not enough energy available to get it up over the obstruction. Okay, now a constriction can be either a step up from the bottom of the channel, or it can be the channel changing its width. And we're going to look at both of those today. So consider here at some upstream location, we've got a channel that's rectangular with a width of 2.5 meters and a depth of 0.9 meters, and it's conveying a flow of 4.25 cubic meters per second. Now, we've got a step, and we want to find out two things. First of all, if we have a step of 0.05 meters, then what's going to be the new flow depth at location 2? And then secondly, how high could we get this delta Z before choking occurs? All right, so the procedure for this is, first of all, we're going to, when we know the step height, find out what would be the V1 upstream so that we can calculate the Froude number at 1. And the reason why we want to assess the Froude number upstream is that if it's subcritical upstream, then that tells us which of the routes we need to select when we solve the cubic equation for the downstream depth. And so that's sort of the reason behind finding the velocity and Froude number at 1. And then when you find the energy at 1, the reason why we're doing that is when you've got a step up like this, it's the energy at 1 minus the delta Z that gives you the energy at 2. And so that's the process by which you can find the new depth downstream, is that E2, of course, is going to be the depth at 2 plus Q squared divided by 2G A squared. And where we've got a rectangular channel like this, then the cross-sectional area is just the width B times the depth at 2, and that's squared. All right, so I'd like you to give that a shot. Try and find out what will be the new flow depth at the downstream location when you've got a step of 0.05 meters. And then for part B, what you're going to do, when it's the maximum allowable obstruction, that means that when you've just come to that maximum obstruction, let me go back to this diagram. This figure C is illustrating the maximum obstruction. This is the biggest step that can be tolerated. And remember, that's the one that's associated with the critical depth. And so we know that in this example, if it's saying what is the delta Z max, when you have delta Z max, then Y2 is equal to YC. So it's the critical depth there. Now I've given you here an easy way to find the Froude number if you've got a rectangular channel. A hydraulic depth is equal to the flow depth if you have a rectangular channel like we've got here. All right, so I think you've got what you need to go ahead and get started. So we're looking for the flow depth, and then if you know the flow depth in part B is equal to the critical depth, then how high can that Z max be? Okay, so if we find the velocity, then that's going to be useful for calculating the energy at 1, because we already know the depth at 1. That factors into the energy. It's the flow depth and then the velocity head. And so if we know this delta Z is 0.05 meters, then we can find out the energy that's existing at 2. So there's going to be less energy at 2 than there was at 1, because that step up is extracting some of the specific energy. So I know the energy at 2 consists of the depth and the velocity head. And this time, instead of writing the velocity head as v, since I don't know the depth, I don't know the velocity. And so I'd like to just have one variable expressing that unknown depth, y. And so that's why here I've got a2, and then that's 2.5 times the depth y. So it turns into a cubic equation that's shown here, and then there are 3 roots to the cubic equation, one of which we can just reject straight away, the negative root. But then of the other 2, one represents a subcritical depth, and one represents a supercritical depth. And so that's why I need to know the Froude number upstream. And at location 1, before that step, the conditions were subcritical, which tells me I need to choose the deeper of those 2 positive depths. And so when the step is 0.05 meters, then the flow depth after the step is going to be 0.804 meters. So this is a process that we kind of touched on last time in class. Now, calculating the maximum step is a little bit different. It's just that instead of the y being the unknown, we put in the critical depth as the y value and solve for the z. Okay, so if we want to go for the z max, then that means that the downstream depth is the critical depth. And for a rectangular channel, we have an easy way of calculating the critical depth. We can just identify the flow per unit width, that's the lowercase q, and by that what we're talking about is, we know the width is 2.5 meters, and the flow rate is 4.25 cubic meters per second. And so this capital Q divided by B, the channel width, gives us the flow per unit width. The units here of 1.7, we can either talk about it in terms of units of cubic meters per second per meter of width, or the meters cancel out and then it turns into meters squared per second. Okay, so we used that flow per unit width here to find the critical depth. And so we're going to set that critical depth to conditions at 2 and solve for the delta z max that causes those critical conditions. So just gradually increasing the depth until it forces critical flow at 2. And what we should get from that is a maximum step of 0.084 meters. So any taller than that, and there just won't be enough specific energy at 1 to push the flow over the obstruction. Now, are there any questions about the concepts here? I don't want us to spend too much time just crunching the numbers, because I think that sometimes we can understand the concepts and the theory a little bit faster than we can do tons of calculations. And since we've got so many examples to get through, I want us to focus mostly on the ideas. So, any questions about the ideas? All right. So that's a maximum step example. The takeaways I want you to remember from that example is that the maximum constriction is the one that induces critical conditions, because that's the most efficient way of getting flow through some cross-section. And if you make any sort of a obstruction that goes beyond that, then the elevation upstream is going to become choked. And so we have to accumulate more energy to overcome the obstacle. Let me give you an illustration of that. Let's say that we have water flowing through a river at a depth of 10 feet, just flowing along. Uniform flow, steady conditions, but now suddenly we place an obstruction in its path. We put in some sort of a wall that's itself 10 feet. And so obviously the water is going to have to pool to get up over that obstacle. If the flow depth is 10 feet, there's not going to be enough energy to get over an obstruction that's 10 feet. And so I introduced in class last time the idea of this notation of primes. And what the difference between y1 and y prime 1 is the prime means after pooling occurs. And so we want to find out, after pooling occurs, what's going to be the new upstream depth. And what we know is that the water depth is only going to continue to accumulate until there's just barely enough energy to get over the obstruction. And so that tells us that it's going to be critical conditions over this obstruction. So we know that it will be the critical depth over this wall, because the water doesn't want to pool any deeper than it has to get over that obstruction with the minimum amount of energy. So here's an illustration that kind of tells you what will be the new upstream depth. Let's say that we had a channel that's rectangular and the width of the channel was 10 feet wide, and we've already seen that the initial flow depth is 10 feet. We want to find the new upstream depth after pooling occurs. So the procedure that we'd go through to analyze this is we're going to be comparing the required energy to the available energy to know if pooling will occur. The required energy to get up over this obstruction is going to be the obstacle height, so this delta Z of 10 feet, and then the minimum energy of the flow. Do you remember from class last time the relationship between critical depth and minimum energy? There's kind of like a quick approximation. It's not an approximation, it's actually, it just works out that at critical conditions, a certain fraction of the flow of the energy exists as depth. 2/3, right. So what we had was E minimum is 3/2 of YC, because YC is 2/3 of E minimum. Okay, so to find the required energy, we know conditions are going to be the critical depth, and then the obstacle height here is 10 feet. Now what about a quick way of calculating YC for a rectangular channel? How do we easily calculate YC? From the last example you did it. Right, lowercase q, flow per unit width squared divided by g to the 1/3 power. And that gives us YC. So this is actually pretty easy to find out how much energy is required to get over the obstruction. It's the height of the obstruction, delta Z, plus the minimum specific energy, which is 3/2 of YC, and YC is pretty easily calculated based on the flow per unit width. So let's take a look at that, the total specific energy required to get over the obstacle. All right, so this shows that. We've got our critical depth that's calculated based on the flow per unit width. So we've got some critical depth, and then we say the minimum specific energy is 3/2 of the critical depth. So this minimum specific energy is how much energy is required just to pass the flow above the obstacle. And so the total energy required is the obstacle height of 10 feet plus this minimum. So we need 16 feet of energy. And if we go back to this drawing here, at location 1, there's 10 feet of energy as the depth. And so it's only going to flow over the obstacle without any pooling if there was an additional 6 feet of energy in the velocity head. And so let's see if that's the case. Let's see if there's going to be pooling. So we have to compare what's required to what's available. The requirement is 16 feet of energy. So the amount that's available initially is the depth and the velocity head. And this is a new way of looking at the velocity head, because we've already said you can find the velocity head by v squared divided by 2g, and there's also q squared divided by 2ga squared. What this is saying is you can also calculate the velocity head by lowercase q divided by 2g y squared. So we've just basically moved the b, the width, from the area up into the numerator there, so it's flow per unit width. It's essentially the same thing. But if we already know the flow per unit width and we're trying to solve for the depth y, then maybe it's a little bit easier to think of the velocity head in these terms. And so how much energy is there initially? Not very much, not enough, because there was the 10 feet as the depth, and then only about 0.388 feet is velocity head. So the conclusion here is that the required amount of energy is bigger than what's available. So there's going to be choking flow, and the water has to pool until enough energy can accumulate to flow over the obstacle. So we need to solve a new upstream depth. So just to summarize, we compared the required specific energy to what was available. And the available was less than required, so there's going to be pooling. Any questions so far? Okay, so then to find the new upstream depth, we're going to set the requirement equal to some y prime and then the velocity head when you've got the new depth y prime. So, I mean, this is actually pretty simple. If you think about, we just keep setting the energy equation at 1 equal to the energy equation at 2, or in this case we're saying we've calculated some amount of energy that there has to be at 1 to get over the obstruction. So if we know that this is how much energy there has to be, we're just trying to find out where the breakdown is in terms of how much of that is in the depth and how much of it is in the velocity head, because those are the only two places that the specific energy is going to be. And so here it's going to be y prime 1 is the depth, and then the velocity head as a function of y prime 1. It becomes a cubic equation again, and then we have 2 non-negative roots. And the way that we know to choose the subcritical root is just because we had previously calculated the critical depth before pooling, and our critical depth, let's see if we got that here, the critical depth was 4.265. And so the initial depth of 10 feet was greater than that. So we had subcritical conditions before, and so it's going to be subcritical again. So we choose the larger depth that corresponds to subcritical flow. Any questions about that method? So that's how you calculate the new upstream depth. Let's skip over this one and talk about channels that get narrower. Now, here is a picture of a river that has some piers supporting a bridge. And what we often need to know about a situation like this is if the piers that we put in are going to cause any kind of a water level change. And especially we're interested in that if it's going to propagate the change upstream and begin to cause flooding that maybe hadn't occurred before this change, or if it will cause the water level to rise and potentially threaten any structures that are built along the banks of the river. Now, whether the water level will rise or falls depends on the conditions, if they're supercritical or subcritical. So we're going to take a look at how a change in channel width is similar to a change in a step up in a channel in terms of it being an obstruction. We don't really know what the behavior is going to be until we do some calculations. So we've already taken a look at when you change the bottom of the channel, where you raise it. That was one kind of obstruction. And when we had an obstruction like that, the flow per unit width is the same before and after the obstruction, because the channel stays the same width as it was before, but you're losing specific energy because the water has to flow up over the obstruction. So here's the previous illustration of where we had a step up, and the E is decreasing, the specific energy, but since the width didn't change in this situation, lowercase q stays the same. But what if the width of the channel decreases? So let's say that you have a wide river that because of maybe the slope of the channel or because of geography, the channel is decreasing in width, so that forces the same flow rate through a narrower channel. that's going to increase the flow per unit width, but the specific energy didn't necessarily change if the channel bottom is the same as it was before. So you don't lose any energy. But whether the depth is going to increase or decrease is once again governed by the conditions upstream. And so we have to know if the conditions are supercritical or subcritical. And if they were subcritical upstream, then they will be subcritical downstream at the constriction, and vice versa. Okay, so take a look at this example. It's the same 2.5 meter wide channel that we've looked at earlier today. The flow depth initially is 0.9 meters. And so we've got a flow rate of 2.25 cubic meters per second. But now, at the downstream location, instead of a step up, we have the situation where a couple of piers are put into place. And each one of these piers is 0.25 meters in width. Let's say that they're circular in diameter. It doesn't actually matter the shape of them. It's just going to be reducing the effective flow width here. And so the flow per unit width is different than it was previously. Because remember that the lowercase q, flow per unit width, is q divided by b. And at 1, the b was 2.5 meters. Now at 2, the effective flow width is only 2.0 meters because the water can't flow through either of those piers. It has to go around it. So we want to know, in a situation like this, what's the new depth going to be when you've reduced the effective flow area. All right, so let's assume that there's no energy losses. And that's just an assumption for now. Later on, we'll start to look at how coefficients of friction can be used to actually account for energy losses. But assuming that there are no energy losses as the water flows around this pier, the procedure for solving this is similar to what we've done in the past, where you find out the flow conditions at 1. You want to know, first of all, the velocity. You want to know what's the Froude number at 1, the specific energy at 1. And then we're going to try and find the depth at 2. And it's going to be the same thing as before. In this case, there's no delta z that we have to keep track of, though. In this case, it's just going to be that we're comparing the let me write this on the board. You'll find the E1 in step 2, and then you're going to set the E1 that you've calculated in step 2 equal to Y2 plus Q squared divided by 2G Y2 times the B. And it's this new B, the B at location 2, that you have to be careful about, because the B at location 1 is 2.5 meters, but the B at location 2 downstream after the choke occurred, the effective flow width is only 2.0 meters. Okay, so this is another one of those where you'll get a cubic equation and you'll need to find which of the 3 routes to select for the new downstream depth. So I'm going to actually give you the time to solve this one so you can get some experience with finding the new flow depth when you've got a constriction that changes the channel width. Okay, if you find the amount of specific energy that it's at 1 before the channel got narrower, essentially, you find that there's 0.951 meters of specific energy at 1. By the way, just as a little side note, a reminder to myself to ask you, why not just use that the energy is 3/2 of y? And that's a pretty nice shortcut. Why don't we just say that the specific energy is 3/2 of the depth? Because conditions aren't critical. That shortcut only applies when you've got critical flow, and here we don't. So we have to calculate the specific energy by considering the depth and the velocity head. So when you do that, you get 0.951 and set that energy equal to the depth and velocity head at 2, where the only unknown is y2, and we get a cubic equation where the roots are a negative root, 0.3197, and 0.865. And we know that conditions at 1 were subcritical without even calculating the Froude number. In this case, we don't have to calculate the Froude number because I had already solved for the critical depth. And remember that another way to assess whether you have subcritical or supercritical conditions besides calculating the Froude number is just compare the flow depth to the critical depth. And our flow depth at location 1 originally, let's see, what was the flow depth there? It was 0.9 meters. And so the flow depth initially at location 1 of 0.9 meters is deeper than the critical depth, and so that means at location 1 the conditions are subcritical. So then that tells me to choose the deeper of these two non-negative roots. And so then we could calculate the Froude number or just compare it to the critical depth, but the depth at 2 should be 0.865 meters. Any questions about that example? All right. So here's another way that a channel can get narrower. It's not just the case of a bridge pier that's obstructing the flow. The channel itself could physically become narrower. So what that means is that the B is decreasing, lowercase b, which is the flow, the channel width at the bottom of the channel. So we've been thinking about in terms of flow per unit width, lowercase q, assuming that these were rectangular. So it's interesting to look at a specific energy diagram and think about how a specific energy diagram changes when you've got a channel that's contracting. Because we looked at how a specific energy diagram can be used when you've got a step. We've looked at that graphical solution before, but what about when the flow per unit width is changing? So let me ask you this. If you have the Q at 1 and 2, the capital Q, the same, then what does that do to the flow per unit width once the channel gets narrower? It increases it, right, because B is getting smaller, whereas Q is staying the same, so lowercase q is going up. So what does that do for the critical depth when the channel gets narrower? If lowercase q gets bigger, then the critical depth is also increasing. So the critical depth is going to get deeper when a channel gets narrower. So consider this figure is kind of showing this curve on the left is the specific energy diagram for location 1 before the channel gets narrower. And then this specific energy diagram here that's shifted to the right and upward is the specific energy diagram after the channel has contracted. And so what you need to remember is that if you increase the flow per unit width, that shifts the diagram to the right and upward. And the reason why it's shifting it upward is because the critical depth is deeper, for the reason that if flow per unit width is higher, then the critical depth is higher. And then the reason why we know that it's shifted to the right is that minimum specific energy is just 3/2 of the critical depth. So if you have a larger critical depth, then that's going to increase the minimum specific energy. So essentially what it does is it translates the specific energy diagram to the side and up. Now, we can use that change to help predict what the new depth is going to be. So we had subcritical conditions in the example that we worked just a moment ago when we were looking at this pier. We had subcritical conditions. And so let's take a look at this figure. We had some subcritical depth at 1, and we go sideways to the specific energy diagram, and the first specific energy diagram, this curve is corresponding to the conditions at 1. So we go down and then we reflect off of the second specific energy diagram, because once the channel contracts, we're going to have a different flow per unit width. And so we can find the new downstream depth by the translated to the side specific energy diagram. So you need to actually graph both of them if you're going to be solving this graphically. Okay, so let's take a look at this, this contraction. Let's have the channel at 1 be 10 feet wide, and we know the velocity of flow, the depth of flow. So with these things we can find out how much specific energy there is at 1, and we want to find out how narrow can B get and avoid choking, because there is some limit. You know, if you make B too narrow, then it's going to start to choke. And in this previous example, we saw that by making the channel narrower, it made the depth decrease. So let me ask you, what do you think is the limit of how narrow you can make this channel width? Like we talked about the maximum limit for, you know, you can make the step a certain limit, but what's going to constrain the limit of how narrow this channel can get? That's a good question. That's a good point. But we're talking about how narrow it can get without choking. Because you're right, if we didn't care about choking, then you can just make it narrower and narrower and the water will continue to pool upstream. What we're saying is we want to make B as narrow as we can. Now, what happens to the water depth as we make B contract? Water depth decreases. Yeah, so when we make, that's counterintuitive, right? That if you make the channel narrower, it's actually making the water more shallow when you have subcritical conditions. That's, I think, sometimes what throws people off is you just would think, well, if you make the channel narrower, then that's going to mean that it has to flow deeper, right? Because maybe you've trained yourself, rightly so, to think in terms of the continuity relationship of, you know, A1 V1 equals A2 V2, and so maybe you're expecting if you make the channel narrower, then it's going to have to make the depth increase. But this specific energy diagram says actually the opposite is true. That when you make the channel narrower, it decreased the depth. So of course the velocity is going up, the velocity is increasing, but the depth is decreasing. So this takes me back to my original question, like what's the limit? How narrow can we make that channel if the depth is getting progressively lower? Critical depth. Yeah, we can keep making the channel narrower and narrower until the depth at 2 is equal to the critical depth. But then if we make it any more narrow, it's got nowhere else to go, because critical depth is the most efficient flow depth, and so then we'd have to accumulate more energy upstream so that we had enough energy to get through the obstruction. All right. So with that in the back of your mind, in this example, what we're going to find out is the minimum B, the minimum new width at 2 that can be used to avoid choking. So here is the energy at 1 is equal to the energy at 2. The velocity head is being written in terms of flow per unit width. And so the hint that I give you is that we want the minimum specific energy at 2 to equal the energy at 1. And then what's the other thing? When you've got critical conditions, then we know that E min is equal to 3/2 of YC. All right, so if you're still stumped by this problem, the first place to start anytime in a problem like this is just calculate how much specific energy there is at 1. And then from there, maybe it will stimulate some ideas. So you got to find out how much specific energy there is at 1, and then remember that we're going to try and make B as small as possible. And as you keep making B smaller and smaller, you're forcing the depth closer to the critical depth. So what we're going to say is that that same amount of energy at 1 is going to be at energy as at location 2, but the depth is going to account for 2/3 of that energy. So we're going to say we want the critical depth to be 2/3 of however much energy there is there. So once we have the depth, then we say any leftover energy is going to go into the velocity head. And so then that's what this next term is. We're saying that the velocity head is going to be the total energy minus the depth. So then you can solve for the velocity at 2. And at this point, the velocity is really moving quickly, 10 feet per second. It has to speed up a lot compared to the 3 feet per second that it was initially, because we've contracted that channel so narrow. But we still don't know at this point what the width is. And so then at this point, we're just sort of playing some algebra with the channel geometry to find out what's the width, because we know the velocity and we know the flow rate. Remember, Q equals VA, so if we divide the flow rate Q by this velocity that we've got, then that'll give us the area. And then we do know the depth component of the area, just not the width. And so if we divide the area by the flow depth, which is that critical depth that we'd calculated, then it tells us the narrowest we can get is 4.17 feet. Any more narrow than that, then the depth simply can't get low enough to accommodate it. So the flow is going to begin choking upstream, and then that means that the water level is going to rise until it's got enough energy. So it's the same kind of pattern for all of the problems that we've done so far today, and that is just comparing the energy at 1 to either a required condition downstream or the minimum conditions downstream, if we're assuming it's going to go to critical conditions. Any questions about that example? So any narrower than that and the flow would start to choke. Why does flow choke? Can't handle the pressure? Okay, that's one way of looking at it. Why is the water level getting deeper upstream when choking occurs? It needs more specific energy. That's the way that the flow, it's the only tool that the flow has to gain more energy, is to get deeper. And another way of thinking about it is that if the flow is choked downstream, that means that you're not getting enough out compared to the in. Remember, inflow versus outflow. So if you've got more flow coming in than the downstream can accommodate, then that means temporarily you're going to have an accumulation upstream. And so the water level is going to be rising because of that temporary imbalance between the inflow and the outflow. So it's kind of a simultaneous thing. As the choking occurs, the energy is accumulating at 1 until there's finally enough specific energy to get up over the obstruction. Questions? All right. Now, in one of the examples we worked today, we assumed that there would be no energy losses during contraction. And of course, that's not necessarily very realistic. And so there have been these empirical ways of trying to characterize how much energy you could expect to see for either a contraction or an expansion. And the loss coefficients are added kind of like a local loss in a way. If you remember when we were working in closed channel flow, we would multiply some k value by the velocity head. This is very similar to that. Here we have the velocity head term, and we're multiplying it by a c value, which is just an empirical coefficient. And there's a pretty wide range. Obviously, the more gradual a transition is, the less energy loss there will be through that section. And so a section that's very abrupt would maybe be on the higher end of this range, and a very gradual, orderly transition where there's less turbulence would be towards the lower end of these expansions. But all you have to do when you're given a c value is just to add that on as an additional term on the right-hand side, because And why on the right-hand side? It's because the flow is going from 1 towards 2, and so c times the velocity head is acting as though it's an energy loss. So we're saying that the amount of energy that's available for the depth and the velocity head has been decreased by whatever losses occur during the transition. So that's why it's over here on the right-hand side of the equation. So let's see. Let's skip over this slide and consider this example of the expansion, where we've got a known flow rate and a known channel width, and we know the depth at 1, and just based on the taper of this transition, we're given a C value kind of in the middle range, 0.45. So if we want to find for an expansion where we are accounting for the energy losses, we want to find out what's the new depth downstream. So remember, what happened when we made the channel narrower? What happened to the depth? It decreased, which was kind of unexpected for us, right? That was under subcritical conditions. Now here, we've made the channel wider, and so like our brain kind of reflexively might say, if you make the channel wider, you're going to make it shallower. But we got burned the first time we made an assumption like that, so we won't necessarily hazard a guess till we do the calculation. So we want to find out what is actually the depth downstream where we've increased the width from the original width of 3 to now 5.7. Now fortunately, there is no maximum width. You know how when you make the channel narrower and narrower and narrower, you might choke the flow? In this case, there isn't like a maximum width that we have to be wary of. So that doesn't complicate things too much. All we have to do is calculate the new flow per unit width, and so we're going to find the energy at 1 prior to the expansion and set that equal to all of these terms, which are going to be based in the unknown y2. Okay, so we've got just enough time for you to do the calculations on that, and we will take a look at the solution in just a moment. All right, so this one, you find the critical depth and then the flow per unit width for both at location 1 and location 2. You find how much specific energy there is at 1. You get the 3 roots, and we choose the subcritical depth because our flow initially, the depth was larger than the critical depth. So we had subcritical conditions at 1. All right, that's it for today. Remember that the next thing on your plate is this assignment is due Thursday. And today's pie day. I'm going to be participating in a pie eating contest if any of you want to witness that or challenge me. Bring it on, because I'm a good eater. So, all right, have a good one. I'll see you on Thursday.